Welcome everybody to my talk, Honey, I Shrunk the Target Variable. So before I start, quick question, who actually gets the reference to the movie? Anyone see? Oh, okay, so I wasn't too bad in choosing this. Yeah, so what inspired me to give this talk is that working as a data scientist, you surely know that you're kind of feature engineering a lot of your time, you're coming up with cool transformation, combining features, and sometimes it doesn't stop with the features. Sometimes you also think about transforming the target variable, right? And this is an area where there are a lot of pitfalls. And when I began my journey as a data scientist, I stepped in some of those pitfalls. And this is why I want to share this point with you. So just a small introduction of myself. So I'm head of data science at Innovex. I have a mathematical background, really care about mathematical modeling, bringing stuff into production, did a few projects in personalization and recommender system. Of course, I'm a huge fan of Python, the PyData stack, and also contributed to some open source projects like PyScaffold, for instance. And I work at Innovex. We are an IT project house with a focus on digital transformation. Yeah, and basically offer everything from app development, UI, UX, IT and operation, and of course also the data part like data engineering, data science, and this is the part where I work in. But coming to the talk, and I want to start with a small little recap about metrics. So when we have any kind of regression problem, right, we have to decide for some proper metric that tells us if it's good or bad, whatever we're going to fit in the end. And there are several metrics, but in most cases, people actually rely on the root mean squared error, right? It's like the most often used metric for regressions in practice. In fact, it's like a default criterion in scikit-learn. And some just use them as a default. And one thing I want to tackle in this talk is to answer the question if it really makes sense in every use case, and also how to decide if something makes sense or not, the root mean squared error, or if one should rather choose another metric. So we'll actually deal with 4 different metrics. So this is why I want to give a small repetition. So what we see here on the upper left is the root mean squared error. Yeah, you see the target y and y hat, our prediction, our estimation, and as you know, then it's squared, and we take the square root. And this is like the quadratic way of judging the difference. You can also do it in an absolute way. This is where we have the mean absolute error. You surely know those two really well. And for use cases where we are rather interested in some relational errors, so to say, where we care about how much we deviate from some given target percentage-wise, there are in the lower row the root mean squared percentage error, where we just divide by the target, and then there's a squared version of this, and also an absolute version, the mean absolute percentage error, shown here on the right. And we're going to use those throughout the talk. So now coming to our actual use case. So imagine I had a beautiful car like this, but gas prices are really high, so I want to sell this car. And in fact, nowadays, people would maybe ask me the first question if the tank is actually full or empty, but just assume that I want to sell this car, and I have no clue about cars, and so I asked myself what kind of price should I ask for. Yesterday we had a nice session of mobile.de. Of course I could use their platform, but let's say I want to come up with something myself. I could come to the idea of fitting a model on a database with a lot of car features and the prices where those cars were sold, so like a database similar to the one you have at Mobile or CarGuru or whatever. And what we're going to use now is the database, the so-called used car database with Kaggle. As I said, we have a lot of different features like vehicle type, model registration date, and so on. And then we use this model to estimate the price based on those features. We're going to treat this as a kind of fair market value, and then if I'm a good seller, I could say I go a little bit below this fair price, or if I'm rather greedy, I could be a little bit above, and let's set this as our use case. And so far, we haven't really talked about the metric. So to get closer now to this question, what metric would actually make sense, let's start with two questions. So assume I had 10 of those cars, and assume that I could get 50,000 for each and one of them. This would be like let's say a fair price. But I'm kind of lazy, so the first option would be I sell 9 cars for 50,000, but the last car for 40,000. Or the second option would be, what if I just rather sell all 10 with a price of 49,000, right? So what kind of difference would this make? In the end, I'm kind of losing 10,000 euro. But if you look at those two options using the root mean squared error, then option 1 would be much worse, because you have this one outlier of kind of a difference of 10,000, and this is squared. So asking yourself this question, you might rather go for an absolute difference, right? Because in the end, we think in a currency, we think in euro, and we don't think in square euro, we think in euro. So this is why the root mean squared error maybe is not the best idea. But then second question, so what if I get 1,000 euro less, assuming that the actual car value is 100,000 or 10,000, right? I would, in the first case, give a discount of 1%, and in the second case of 10%. And I mean, the way we are bargaining, like going 10% down is a lot more than 1%. So if we look at this question from the perspective of our different metrics, we might say that, yeah, well, for the root mean squared error or mean absolute error, this makes no difference because it's, in the end, the difference is 1,000, but percentage-wise, it makes a lot of difference. And so this is why, for this use case, for our use case, a good metric would maybe be the mean absolute percentage error. And I think it's important to ask you those kinds of questions if you use different metrics, if you do a regression, if you have a regression use case at hand, because this is how, in the end, your users will see your data product. But yeah, this is already the first, the key learning, that the right metric really depends on your use case, and of course it will also affect your results. So depending on what metric you're going to choose, your model will come up with other numbers. So it's important to ask you questions like this whenever you are dealing with some use case. Now imagine that we actually go for the root mean squared error, because yeah, it's the default in many of the scikit-learn's estimators. And what does it actually mean, the root mean squared error? And this is going to be the only mathy slide here. I couldn't let it go. So what happens if we take the root mean squared error here without the root, so that it makes no sense or makes no difference in this case? If we express this continuously as a continuous random variable, our target, so assuming we keep the features fixed, and assuming we have a whole density, then the sum becomes an integral. We have to include the density over our targets. And if we want to now minimize this, it's like what we always do. We derive, set it to 0, and in the end, we end up having y hat is the integral over y times the density. And this is actually the definition of the expectation value, right? So the definition of the mean. And this is really interesting because so whenever you're minimizing for the root mean squared error or just the mean squared error, you're actually trying to estimate the mean of your residual distribution. And this is a really important thing to keep in mind and will come up also later. There's an analog proof for the mean absolute error. In this case, you are looking for the median. And this is really important to keep in mind when you're choosing a metric. So for the math skeptics, I mean, there's some out there, you can also try this out. So the root mean squared error, and let's say we take the price as y and just use this on this Kaggle data. So we just take our whole prices, and we use scikit scipy to optimize, and we see that it's actually close to some rounding error to the mean, and the same goes for the mean absolute error and the median. So this is the case. So far, we haven't done anything to target variable, right? We haven't transformed it in any way, but these values will come up also later. So second key learning here is now that, as we said, the mean, so the expected value, minimizes the root mean squared error, and the median minimizes the mean absolute error. So now to the actual topic of the talk. Now, what happens if we start playing around with a log? If we start shrinking the prices? Because if we look at the distribution of prices in our use case, well, this looks like a log normal distribution, and even if you fit the log normal distribution to the value, you see it's not really perfect, especially here. This will be important later, but you might come to the idea, well, there may be outliers and it looks a bit skewed, so why not just use the logarithm or apply the logarithm, and the data will look better. So let's just try this and see what happens. So what we're going to do, we take the log of the price as our new target variable. We're going to minimize using the root mean squared error again. So this is, you can think of this like a model with only an intercept in a way. So far we haven't used any features. And then we transform the whole thing back. So let's just do this as before. So this time we take the log, you see here. Then we do we optimize, we minimize using the root mean squared error. We get 8.3, and then we transform it back, right? And we end up having around 40,000. So for comparison, the numbers we had before, the mean was actually 6,800. So we are completely off. We are rather really close to the median, and this is, at least when I saw this the first time, was to my surprise, really, like the median. So, okay, I transformed, I minimized, I transformed back, and now I'm having like optimized another metric. It was like I would have optimized for the mean absolute error. And so this really got me questioning, so, okay, what happened here? And then when you now do the math and actually calculate what happens, like transforming and minimizing, transforming back, at least for log normal residual distribution, you can easily prove, and you find all this also in the blog post to this talk, that taking the logarithm, minimizing for the root mean squared error and transforming back will lead to the median. So if we were really interested in the mean, then we would have to correct this by adding 1/2 sigma square. And we can also try this out for our data, which is not perfectly log normal. And there, sigma square, so the variance in this case of the residual distribution, if we add this to our estimation, y hat, and apply the exponential function, then we are a little bit higher than the actual mean, but this is due to the fact that it was not log normal, but we see that we are much closer and that we have kind of corrected this. And of course, you can ask now for every of those metrics, what happens if I do this like transform, minimize, transform back, and if I'm actually interested in another metric like the mean absolute percentage error or the root mean squared percentage error. And in all those cases, I have to apply different corrections. Given, of course, I'm always assuming a log normal residual distribution that you don't always have in practice. So this is why these differences come. And yeah, so if you're interested in all the math behind this, it's here given on the blog post. And so the third key learning that we have now, that we saw that transforming your target might actually change what you're minimizing. This is really important to keep in mind, that be careful what you evaluate and what you train, and if you in between kind of transform your target variable, then this will, in most cases, except of the mean absolute error here, the correction is 0. In this case, it makes no difference, but for all the others, you have to correct. So now, can we use this actually to help us? Can we maybe gain something from this nice insight? So what if, for instance, some metric is not supported in our favorite machine learning library? So assume that you want to optimize for the root mean squared percentage error, and it's not available, but you only have the root mean squared error. This was, for instance, in the case in a nice Kaggle contest 6 years ago. The question they asked was to somehow predict the sales in Rossmann stores, and the evaluation was in the end done with the help of the root mean squared percentage error, and all people kind of asked, so okay, how do we do this now, right? Because at least scikit-learn, I'm not sure if it's still the case today, but at that time hasn't had this, so you could not just say, I directly want to optimize for the root mean squared percentage error. So again, what we could do instead of just fitting the model and using the root mean squared error as a loss and evaluating the prediction with another score, another metric like the root mean squared percentage error, we could, as we have just learned, first take the logarithm, so transform it. Then we fit the model using the root mean squared percentage error, and then we choose the corresponding correction and go back. And this trick kind of helps us then to have actually minimized a metric that our machine learning library doesn't even support. And so I did this for the use case that I just showed. This time I used all the features, did some random forest on these features, and checked what happens if I have the raw results, and compare this with the root mean squared, the mean absolute error, and the MAPE and the SMPE, and compare this now percentage-wise to the log transformation and doing the correction. And this is what you see on the y-axis. So let's just, I think it gets easier to understand if we just look at the first column. So assume I do the log transformation, I fit with root mean squared error, I transform back, and then I look at the results using the root mean squared error, then I'm actually worse than if I had not done this transformation. I mean, this is what we saw before, that we would actually need to do a correction, but since it's not perfectly log normal, we are even getting worse. And so positive numbers mean a deterioration, and a negative percentage number mean an improvement. So this tells us that if I would be really interested in the root mean squared error, doing any kind of transformation is actually bad, right? So we end up being worse than not doing any transformation. And if you wonder about the last row, so this is a fitted correction, of course, you could, instead of doing the mathematically correct correction, you could also use some holdout set to minimize this one parameter to get a kind of a fitted correction. This is why the last row is always better. So now what happens with if we were interested in the mean absolute error? In this case, we see a slight improvement. This is also what we have seen. So what is also proven, that if we take the logarithm, if we go back, then we actually arrive at the median, And this is like optimizing the mean absolute error, so we see slight improvements. In this case, the sigma 2 correction is also 0, as we've seen before. And using a fitted correction gets us a little improvement. Where this becomes interesting and maybe also intuition-wise interesting is if we look now at the percentage errors. I mean, this is already the intuition, right? Because you, going into log space kind of makes absolute relations rather in relative relations. So just applying the logarithm without any correction improves us by almost 11%. Using the correct back transformation and correction, it's a little bit better, and fitting it gets us even 2 more percentage points. Where it now really shines is if you look at a metric like the root mean squared percentage error, like it was asked in the Kaggle. Here, doing the no correction gets us an improvement of 12%. Using the mathematically correct one is 28%, and even fitting gets us even more. And this was in the Kaggle competition like the key ingredient to win this Kaggle competition. So the winner back then wrote a really nice blog post about all the tricks he applied and also showed how he mathematically derived this correction, what I showed before. And it was, like I said, one of the key ingredients, so you could not win it without using it. And this is what really intrigued me in this case, that in one way it's a pitfall. You should be always careful, but if you know what you're doing, then you can use it for your advantage. And with this message, I want to actually close this talk, so please think before you shrink. And yeah, if you want to know more, so as I said, there's a whole blog post with a lot more information about this, and you can also try out all the code I showed in Jupyter notebooks and run it for yourself. So thanks a lot for your time and your attention, and thank you.
Thank you a lot, William. Super insightful talk. Let's go to the questions for the audience. Once again, we are in Slido. What do you think about linear transforms or other nonlinear ones, like box, cox, or etc.?
For the linear ones, so affine transformation, you're pretty safe. So it's always difficult when you're using non-linear transformation. Then you run into trouble that those things apply. For affine ones, like the one you always do at deep learning, that you're normalizing and whatever, and standardization, there you actually don't fall into this trap. So it's basically most of the time the logarithm. And with box cox, I would also assume that you have to be really careful then, because you're really transforming a lot. So, but I haven't done the math on this, but pretty sure that you have to be careful.
All right, next one. What is your opinion or experience on capturing skewness by modeling a log normal distribution explicitly? For example, by maximizing the log likelihood.
So we did this a few times, especially so log normal distribution is quite often you use it if you have some kind of sales value, for instance. There you can use it. The problem always are the outlier, and I mean, the question is again the use case. So what is it that I'm really interested in? So if I have a log normal distribution, I would maybe argue from the beginning that I am more interested in getting the median of the residual distribution, and then I would apply the logarithm to eventually minimize the mean absolute error, again due to the fact that maybe the use case is like this, that you're trying to optimize the number of some goods that you need to predict for optimal demand planning, and you don't want to throw something away, and then quadratic difference just makes no sense in many use cases. But yeah, I would say it really depends on the use cases, and if you, if the use case needs it, then the log normal distribution is fine. So for a lot of Bayesian models, I also used it. So yeah.
All right, let's go to the next one. How do you compute MAPE? How do you deal with exactly zero values?
That's a good question. Yeah, with exactly, so if the target is exactly 0, of course, then you would divide by 0, which is problematic. I mean, sometimes you can argue that you have a certain offset, but that you can just apply that you add some offset to your target to avoid this. But again, this also depends on the use case, if this is allowed or if you run into an error. But yeah, percentage-wise, of course, yeah, it's makes no sense. So you have to be really careful if you maybe have some zero inflated stuff with a mean absolute percentage error. But yeah, offset. I would first try to think of an offset or find out if the metric makes sense in this use case if we're dealing a lot with this.
Next one. How do you combine strong skewness with zero inflated distribution, as log becomes then impossible?
Again, zero skewness with zero inflated.
Yes, how do you combine strong skewness with zero inflated distribution?
Yeah, it's a tricky question. So I would have to look also up how to do this. So I cannot really answer directly. I mean, depending on the use case, you could also maybe, yeah, find out. I mean, zero inflated distributions is a really complex topic to model itself. And then if, again, you have maybe a lot of outliers, yeah, I would have to look this up myself, actually.
Let's go to the next one. We have 2 minutes left and 3 questions. How would you decide whether or not to transform your target variable? Non-linear transform will change the data itself, while linear ones just might help opt. Does it?
Just might help.
Help opt. That's unclear for me as well. So the last sentence is, non-linear transform will change the data itself, while linear ones just might help opt. Maybe to opt out. Okay, let's move on to the next one. Who asked the question can reach out to the speaker afterwards.
Is the person here maybe? Then no, help opt.
I think you meant help out.
Help out, okay.
Yeah, maybe it's a typo. But let's move to the next one,
yeah.
And then he can clarify. Log x plus 1, or how do you deal with log 0?
Yeah, this was, again, like similar to the percentage-wise. So if you have 0 data in, then you cannot divide by 0. And yeah, this log1 x plus 1 is quite often used and also available in most arithmetic libraries as an extra function. But then you also have to ask yourself, how am I changing what I wanna achieve in the end? So, yeah, can only say that this is an option. Depends on the use case, as always.
Yes. So let's go to the last one in our last minute. The correction makes the RMSE worse, right? Yeah, I think. Not sure if you already answered that as well, or if it makes sense.
Yeah, I think this was what here. Yeah, I mean this kind of, when I first saw these numbers, it also surprised me, because in this case you would assume to see like 0, right? Because we just mathematically proved that it's that you should end up with the mean again. But the thing is that at the beginning we saw that the distribution, I mean, it looks quite log normal, but it's far from being perfectly log normal. And this was the distribution over the whole data. So this is only a residual distribution if we take a model with only an intercept. But the actual results I showed was a model where I used all the features, and then I have no plot of the residual distributions, but also in this case it was not perfectly log normal, and this explains why it was worse. So you cannot really assume that you have a log normal residual distribution. So the main takeaway here is, if you really want to have the root mean squared error in the end, then don't do some kind of log transformation.
All right, we are out of time, so direct your questions directly to the speaker afterwards. And let's give a last round of applause for William. Thank you a lot.